Myself, Dr. Nitin Gramopadhye, working as Assistant Professor in Department of Humanities and Sciences, Walchand Institute of Technology, Solapur. Today we are going to learn one topic, phase rule, and the learning outcome for today's session is that at the end of this session, students will be able to describe the different terms involved in phase rule and also explain one component system with a phase diagram. This is the particular content that we are going to learn in today's session. First of all, we will see the introduction part for the phase rule chapter, what the phase rule exactly, phase rule equation we'll see, and then we'll see what are the different terms involved in phase rule equation. And then we will apply the phase rule equation for one component system. The behavior of heterogeneous system with respect to changes in pressure, temperature, and concentration was first studied by American physicist Gibbs in 1874, which is also known as Gibbs phase rule. Therefore, the phase rule is an important generalization dealing with the behavior of heterogeneous system. So in short, what we are going to learn here, so the effect of the various parameters on the behavior of heterogeneous system, how the heterogeneous system will behave with respect to the external parameters. The phase rule describes the possible number of degrees of freedom in an enclosed system at equilibrium level in terms of the number of separate phases and the number of chemical constituents in the system. So how many number of components are there and what is the number of phases that the system consists of. The phase rule may be stated mathematically as below. F is equal to C minus P plus 2, where F is the number of degree of freedom, C is the number of components, and P is the number of phases. Now we will see whatever the terms we have involved in the phase rule equation. So here just now we have observed the phase rule equation, that is F is equal to C minus P plus 2, where F indicates the number of degrees of freedom, C indicates the number of components, and P indicates the number of phases. What do you mean by phase? It is defined as any homogeneous part of a system having all physical and chemical properties same throughout. The states of the matter such as gas, liquid, and solid are also known as phases. A system may be consisting of one or more phases. Therefore, a system consisting of one phase only is called as homogeneous system, and a system consisting of two or more phases is called as heterogeneous system. At the same time, if you take the second new example, that is non-miscible liquids, mixture of two or more non-miscible liquids on standing two separate layers. It gives you two separate layers because by nature they are non-miscible. So when we shake the test tube and when you allow to separate it, after particular time it gets separated into two layers. Hence, the such system consists of two phases. Example, chloroform plus water. So whenever the chloroform is mixed with water, the test tube shows the two different phases. So non-miscible liquids causes the number of phases is equal to 2. Now we'll see the next component term involved in a phase rule equation. It is defined as the least number of independent chemical constituents in terms of which the composition of every phase can be expressed by means of a chemical formula or equation. So what is the number of chemical formulas we require to express the combination of the phase is called as the component. To understand the above definition, we'll see some examples. For example, the water and sulfur system. Water system has three phases such as ice, water, and water vapor. The composition of all the three phases is expressed in terms of one chemical formula, that is H2O. Hence, the water system is a one component system. Hence, the water system is a one component system. If you take the sulfur system has four phases such as rhombic, monoclinic, liquid and the vapor. The composition of all these phases can be expressed by only one chemical formula, that is S. Hence, the sulfur system, though it exists in a 4 different phases, still it consists of the component value as a 1. Now we'll come to the next example, mixture of gases. A mixture of gases, for example, oxygen and nitrogen, causes one phase because both the gases are miscible, but the phase is one. What about component? Its composition can be expressed by two different chemical individuals such as O2 and N2. Therefore, the value of component for a given example is 2. Now, the third term involved in a phase rule equation is the degree of freedom. It is represented by capital F in the phase rule equation, and it is defined as the least number of variable factor such as concentration, pressure and temperature, which must be specified so that the remaining variables are fixed automatically and the system is completely gets defined. So to define any particular system, what is the least number of variable that can be required to express so that the other variable get automatically fixed is called as degree of freedom. A system have the degree of freedom F is equal to 0. The system may have the degree of freedom F is equal to 1. The system may have the degree of freedom F is equal to 2. A system is defined completely when it retains the same state of equilibrium with specified variables. For example, a mixture of pure gas. If the values of pressure P and temperature T be specified, volume V can only one definite value or that the volume is fixed automatically. Hence, a system containing a pure gas has 2 degrees of freedom. So whenever the pure gas is an example, we can vary the two variables. One is pressure and another is temperature. The volume get automatically fixed. A mixture of gases where the value of the F is equal to 3. Water and water vapor system where the value of the degree of freedom is equal to 1. The system water in equilibrium with the water vapor has two variables, temperature and pressure at definite temperature. The vapor pressure of water can have only one fixed value. Thus, if one variable is specified, the other is fixed automatically. Hence, the system water vapor has 1 degree of freedom, that is. Now we'll come to see the one component system. For one component system, the phase rule equation is F is equal to C minus P plus 2. Now as the title is one component, the value of the C becomes 1. So we'll keep the value of C 1 in an equation and we'll get the situation F is equal to 3 minus P. Therefore, the three different cases can be arised. Case 1, when only one phase is present. Now we are looking to phase, component is C. So F is equal to C minus P plus 2. F is equal to 1 minus 1 plus 2, and therefore for the given case where only one phase is there, the value of F goes to 2. Thus the system is 2 degree of freedom. It can be completely defined by specifying the two variables such as temperature and pressure. Case 2, where two phases are in equilibrium, where only one phase is in equilibrium, we have just now observed, and now we are observing when the two phases are in equilibrium where we are getting the value of F is equal to 1. Similarly, at case 3, whenever the three phases are existing and if you keep the value of 3 as a P value in an equation, we are getting the degree of freedom 0. What is the meaning of that? The system has 0 degree of freedom. Therefore, the system is defined completely and no further statement of external condition is necessary. Thus, a three-phase system is shown by point C on the graph. This is the phase diagram for one component system. Particularly, this is the example of a water system where we can see the area denoted by the solid area, where the area is denoted by the liquid area, and where the area is denoted by the vapor area. So curve OA is the vapor pressure of water. It represents the vapor pressure of liquid water at different temperatures. Therefore, the curve OA terminates at A where the liquid water and water vapor are distinguishable. from each other, and therefore by keeping the value of f, that is p is equal to 2, we are getting the value f is equal to 1 for all the three curves such as OA, OB and OC. Now we are looking areas. The areas or regions between the curves shows the conditions of temperature and pressure under which a single phase ice, water or vapor exists. So if you look to the phase diagram, what we observe, in one area only one phase is there, either solid, either liquid or either the vapor. So three areas are there. For example, area AOC represents water, area AOB represents water vapor and area BOC represents ice. So any area consists of the phase 1, and by keeping the value we are getting the degree of freedom. Then as the three areas have one phase and one component. Now we'll see the triple point. The curves OA, OB and OC meet at the point O, where all the three phases coexist in equilibrium, and by putting the value of three phases we are getting the degree of freedom f is equal to 0. It means that to get the triple point all the three variables are standard, fixed, no possible degree of freedom is there, all the values are standard, then only we'll get all the three phases are in equilibrium with each other. So all that I have prepared by using a textbook of engineering chemistry written by Jain and Jain. Thank you.